I should first congratulate you to come that far. This is the very last lecture on supervised learning based on um, an introduction to statistical learning textbook. So you have learned a lot of techniques by now. You have one thing to add to the tools that you already have. So I'm very proud of you if you have watched the earlier videos and you're now watching this very advanced technique. This is a technique that has been invented by computer scientists in 1990s. And it was somehow computationally extensive, but by the advent of newer computational power and newer computational techniques, nowadays support vector machines are everywhere, specifically in classifications. The basic idea behind it is to identify two classes by finding a plane that separates two classes. So the basic idea behind support vector machines is finding a plane that separates the classes in feature spaces. So we should first define what is separate. What do you mean by separation, and what do you mean by feature space and dividing things into feature space? So let me explain what a hyperplane or plane is and how we deal with that. A hyperplane in p dimension is a flat affine. Affine means linear combination, subset of dimension p minus 1 value. For example, beta 0 plus beta 1 x1 plus beta 2 x2 up to beta p xp equal to 0 is a hyperplane of dimension p. So in p equal to 2 dimension, we have a line, simple affine line. So let's see why. For example, when I write beta 0 plus beta 1 x1 is equal to plus beta 2 x2 is equal to 0, I can rewrite it as beta 2 x2 is equal to negative beta 0 plus negative beta 1 x1, or we can write just x2 is equal to negative beta 0 divided by beta 2, negative beta 1 divided by beta 2 times x1. I'm sure you know that this is an affine line, so we can just rename it to y is equal to, let me call it alpha 0 plus let me call this alpha 1 x. So that's the line, right? So when p is equal to, that's a simple line. If p is equal to 3, that's a plane. And if it's p is more than 4, it's called the hyperplane. So these betas, beta 0 to beta p, are called normal vectors. So you can have a lot of these. So if beta 0 plus this is equal to 0, 2 times beta 0 plus 2 times beta 1 plus 2 times beta 0 will be equal to 0, right? So if you multiply all the coefficients by same constant, it will become 0 again. So let's fix our choices of beta i's to 1, then will come a normal vector with norm 1. So these are called the normal vector that defines the whole my whole line, and if the summation of the squares are equal to 1, then that is called a normal vector. Okay, that's orthogonal to the surface of a hyperplane. Let's see what orthogonality means. So here, this blue line is 0.6 x1 plus 0.8 x2 minus 6 equal to 1.6. Okay, so it's 0.6 x1 plus 0.8 x2 minus 6 equal to 1.6. So this is the blue line. Why do you see a negative slope? Because if you have two positive things, if you take the other one to the other side, you get a negative sign. So that's why you see this this is negatively sloped curve. Any point that is on this line will, so any x1 and x2 that you choose and is in this line, on this line, for example 6 and 3, 6 and 3, makes this oh, I'm sorry, this is equal to 0. I'm really sorry, this is not equal to 0.6, this is equal to 0. So this line, this blue line is this. It's 0.8 x1 plus 0.6 x2 minus 6 equal to 0. Any point you choose here, like 6 and 3, will satisfy this condition. So any of these blue points are satisfying this line. Also, look at this value, 0.6 and 0.8. So if you draw a line based on the vector of 0.6 and 0.8, basically find 0.6 and 0.8 and just draw a line out of it. That's the easiest way I can explain it to you. Or let's multiply it by 5, we get 4 and 3. So as you can see, this red line passes 3 and 4. You see that? I'm sure you are. 3 and 4. 3 and 4. So this is called the orthogonal norm of this function. So this is orthogonal. So that's the value of beta 1 and x1. That makes it an orthogonal line to it. That means there is 90 degrees angle between the norm and the line or hyperplane itself. So once we have that, we can do a lot of things with it. Specifically, when you set this to, specifically when you set beta 1 and beta 2 such that 1 squared plus the other squared becomes 1, then we get a lot of great properties. For instance, look at this line. This line can be defined, it can be shown that it's is on the line like this, which has same beta 1 and beta 2, but instead of 0 it's equal to 1.6. So whatever you find here that satisfies this point would be the orthogonal distance of that line in here. So this is equal to 1.6. So in a sense, any point you have on top of the in top right of this line can be defined as beta 1 x1 plus beta 2 x negative 6, the same coordinates of this line, equal to the distances of it in a positive way. Any line you have here underneath this line to this point can be defined as same thing equal to a negative value. In other words, the distance of any point you have which is on top left of this line, this blue line, will have this positive distance. Any point that is not on this line will have a negative distance from it. For example, a point like this is beta 1 x1 plus beta 2 x1, where beta 1 was 0.8 and beta 2 is 0.6, equal to negative 4. That means the Euclidean distances of this point and this line is negative 4. Okay, so anytime we are in this region, we have negative distance. Anytime we are here, we have positive distance. We are going to use this property a lot later. So let's define separating hyperplane. A separating hyperplane is a plane or a affine line or a affine hyperplane line that separates two groups or two categories into distinctive categories. For instance, let's say we have this blue and red categories. So we have this blue and this red category. This hyperplane, this black hyperplane, has separated our observation into two distinctive groups, right? So that's separating hyperplane for this group. Here, for the same data set, we can define two more hyperplanes that divided into two distinctive groups. So a couple of questions may come in mind. First of all, what if there is no hyperplane at all? What if we have some mistakenly we have some purple dot here? We cannot find a hyperplane that separates these two groups into two distinctive groups? That's the first question. Second question is, how can we decide which hyperplane is the best? Here we have three options. Which one is the best? How can we decide on that? We are going to answer all of these questions step by step. So hold on to your question for a bit. So let's see what the hyperplanes do. What hyperplanes do. They basically are methodology that finds this hyperplane. So this is the coordinates of this hyperplane. So if you put points in it and they will give you a positive value, since we said for any positive value we are at this side of the line, for any positive value we assign the category to one category. For any negative one we assign it to the other category. So that's how hyperplanes work. We can also define it from one category to +1 and one category to -1. And if we do that, since anytime it's positive, we can assign it to positive, and since anytime it's negative, we can assign it to negative. The product of the classification times this will always become 0, or more than 0. Yi's times this is always more than 0. Why? Because whenever it's negative, we assign it to negative points. Negative times negative is positive. Whenever it's positive, we assign it to +1, so it becomes. So a separating hyperplane is a hyperplane that has this characteristic. Yi times the hyperplane is more than 0. So ideally, we want to find a plane that separates it completely, and we want to find the best one. So how should we find the best one? One of the ways to find the best possible model, if that's the first time you're watching this video, I suggest you disregard this part for a second. This is the Greek version of what I'm going to explain in English now. So please keep it for yourself. Disregard that part. Put your hand on this part of the screen. So let's define what the best hyperplane is. We have a lot of choices. One is to look at the margins, and what margin is the distance that my hyperplane has from the closest point of each category. So here we have these margins, and these margins, both of them have same distance from our closest observations. So if we would choose, let's say, this line, sorry, this is not a line, but assume that's a I'm very sorry for this curl, and it shouldn't be curvy at all. So let's assume that's an affine function. So if that's an affine function, we see this will be closer to purple categories than blue ones. The difference of this and the blue one is so much, right? So this would be the margin of this line from this. So ideally, the best model of this affine function is the one that has the maximum amount of margin from all categories. So maximum amount of margins from our categories. If it's too close to one, it will automatically be far away from the other one. So the one that balances the two are the one that is considered as the best. So let me erase the mess I made. So okay, good. I don't know why my eraser does this, but anyhow, I think that's not too bad. Okay. So here you want to find this line, and the way we find it is through using mathematics. So we are going to use this Greek representation of what we said. It looks scary at the beginning, I agree with you, but after I explain what it does, it becomes clear. So we want to maximize our margin. So M stands for margin, by tuning our affine hyperplane. Remember, we can define a hyperplane by finding its values, beta 0, beta 1, beta 2. So here, since it's two-dimensional, so it's beta 0, beta 1, and beta 2, we want to find that. Remember, I told you that we want to set the norm of the variables we have to 1. So that's how we do it. So that's we make sure we set it to 1 so that we always have one choice, not more, for betas. And then here is classification. So here it says, if you set it 1, this beta 0 plus beta 1 times x IP gives you the distance. So this part of the equation, this part of the equation, gives you the distance of your observation and of course the hyperplane you define times the classification. So this way, when you multiply this, because it can be negative or positive. If it's negative, if you multiply it by its correct classification, which was negative, it will give you a positive number. If it's positive, if you multiply it by 1, it's still positive. So basically, yi times this gives you the positive number, which signifies the distance of your observation and this line. We want that to be more or equal than f. So we want to find the maximum of this distances that we can find. So basically, the only observation that will be counted towards the optimization would be the ones that are closest, because these are so far away. So the smallest distance we can find, which is still, so that is the smallest, largest distance we can find. That is the largest and smallest distances we can find. Because if we change this line, it will be closer to 1, will be so let me do that. So let's see what will happen if we change this line to, say, this margin. So let's assume this dashed area was our hyperplane, okay? So in that dashed area, the smallest distance we have from this line, from both groups, is this 0, right? Because we have one observation right on the distance. So the maximum of this m we can find is this black affine line, and m shall be more than 0. So that is how that is the mathematical description of how you can separate these two classes while keeping the maximum distance from the hyperplane and its closest observations in each group. And these dashed line, which signify the closest observations, that comes from m. This is the line parallel to your affine line with distance m, are called margins. So I'm not getting into too much detail of it. This formulation has very nice properties, and in order to solve it, you have to use SVM, which is support vector machine, in package very weird name E1071. Okay, we are going to work on it in our lab. But what will happen if we have non-separable data? What can we do about that? How can we deal with such a problem? Because there is no affine line that can separate them completely. So, or what if we have a noisy data? For instance, this is the best hyperplane we can find in part left side of my picture, right? So this is the hyperplane we have here. It separates these two data. But if we have just one more observation here, this hyperplane will be changed a lot. What if this was an error? Then we will get a very naive hyperplane. So that will be a high leverage point now. So what do we do with this noisy data? In order to deal with that, we have to use support vector classifiers class, which use soft margins. That means it let us have some errors. So the idea here is, before we didn't let the margins, so before we would make sure the margins will not have any observation here. So now we let margins have these observations inside, and each time it has it, we put some penalty on it. So here, look at this 8. 8 is inside its margin, so it is classified correctly in this classification problem. It's at the right side of the classifier, but it's inside the dashed area. So does 1. 1 is classified correctly, is inside it. So if we have this margin, that's a soft margin, right? Why? Because it doesn't put too much penalty of the fact that it's within the margin. Now let's look at the second class. Here 1 and 11 are both within the margin, right? So look at bar. This was the margin for red area. 1 is classified correctly based on this affine function. 11 is classified incorrectly. 8 is inside the margin, so that's one penalty. But 12 is not only inside the margin, but also is in the wrong direction of classification. So let's see how we can find a softer margin that takes care of these irregularities. Again, we want to maximize the m, same as before. We want to find a margin that has the largest distance from the closest observation in each class. However, we define closest observation to each class in a different way. So first, let's fix the norm of the classes here, the norm of the coefficients of our affine hyperplane here. Second, we have the same thing we had earlier at the left-hand side of the coefficients. Remember that signified the distance of observation, what it is. Here we have m, but by multiplying it to penalty, multiplying it to some being loose, better say, we fixed the cases that are not inside the margin or they are misclassified. For example, if epsilon is equal to 0, so if epsilon I is equal to 0, then you have the simple classifier method we had earlier, right? So because nothing will change. If epsilon I is between 0 and 1, that means classification was okay, but is inside the margin. Inside the margin. For example, 8 and 1 in this example have epsilons that are between 0 and 1. Because if it was 0, then no such margins will be chosen, because you wouldn't let that happen. Now here, epsilon is somewhere between 0 and 1. They're classified okay, because they're in the correct side of classification, but within the margin. If epsilon is more than 1, for any of these observations, that means they're misclassified and are on wrong side of they're within margins. They're inside margins. For instance, 12 here is clearly in the wrong side of the affine line, so it's misclassified and is also the wrong side of the margin. So does 11. 11 is in the wrong side of its margin and it's misclassified. So these epsilons are tuning parameters that we have, and they're always more than 0. And you make sure the summation of them is less than a constant. So this is the budget. That is the tolerance level you have. You can set it. So that is budget. You can set C. If you set C to a very large number, you tolerate all the irregularities that are there. So you let your margins be too wide. If you set C too little, specifically you set it to 0, then you make sure all epsilons are 0, and that's the strict case we had earlier in maximal margin classifier. So by tuning C, you tune the performance of it. So the choice of C is important in classification, and that is why we have to use our test set to tune this C. Here we have some examples. Here, top left, C was very large. That's why our margins could grow as much as they wanted to. Here C is relatively smaller than this one, but larger than the other two. And as you can see, so here, from here to here, then here, and then here, C decreased. And as you can see, the margins decreased. So what is the good size of C? It depends on the test data. So if this is your test error, and this is C, if you observe something like this, you have to choose C that is this much, right? So as always, as before. Another question that has been asked a lot is, what if things are not linear at all? For example, let's say this is the hypothetical case. Let's say this is and we have two classes. One class as this purple one, and one class is this blue one. The purple one is right in the middle, and these are the blue ones. There is no affine function that can separate these two. How about this? It looks like a classification like this is the best one that we can get, which separates these two classes perfectly. But unfortunately, no linear classification will work on that. One of the tricks that you can make is to add nonlinear terms to your classifications. For example, you can consider any value of coefficients here. For example, quadratic, cubic, or interaction, or so on and so forth. And you make that linear. For example, this is that is a quadratic functional form on x1. It has x1, x2, x1 squared, x2 squared, x1, x2. So that's again a hyperplane. This is degree 5, but since we only work on the projection of that in 2 degrees, we get nonlinear shapes. So that to make it more clear, let's assume we are working in, we have 3 functions like this, and we have, so let's call it x1 and x2, and let's call it x1, x2. And let's say our shape looks like something like this. So that curvy case. So if you project it on our x1, x2, on x1, x2 plane, we get pictures like this, which are completely this projection, which comes from this hyperplane, is completely nonlinear. So by adding these nonlinear terms, the point I want to make, by adding these nonlinear terms, we can get rid of nonlinearities that exist there. For example, for the same data set, if we use nonlinear curves, that would be the outcomes we would get. We would get, these are the separating hyperplanes that we have with their corresponding margins. And as you can see, they did a very good job. So, and that is for cubic polynomial. A cubic polynomial has this shape. There are 9 parameters to be estimated, x beta 1 up to beta 9, and it was just put on the formula of the subfork vector classifier we had earlier. One of the problems using these classifiers is if you go more than so for example, if you use more polynomials, the number of parameters we have to estimate would grow significantly, and computationally it will become very, very hard to solve that maximization problem. One of the tricks that mathematicians figured out to solve such questions is using kernels. Using kernels are wonderful because By using kernels, you can definitely do wonderful things, including um, using so much smaller computational power to solve the questions that we had earlier. And the mathematics behind kernels are inner products. To remind you, inner products of two vectors like this, let's say we have these two vectors, 4, 5, and 6, is 1 times 4 plus 2 times 5 plus 3 times 6. That is the inner product of the two. So if you have vector x1 and x2, the inner product is shown this way. So this is the notation that explains the this is this way. Okay, inner product of x1 and x2. So inner product of two vectors are just summation of element by element multiplication of the vectors. It's not too hard to show that the linear support vector classifier, the ones that we discussed earlier, has this functional form for every x. Is the inner is beta 0, which is the constant, plus some parameters which needed to be tuned, times that observation, same observations, inner product by all of the observations you had. So there will be alpha 1, the inner product of x and x1, alpha 2, inner product of your observation and x2, alpha 3, and so on and so forth. So that's what we have. And these are the things we need to have. And that's why we take care of that. So that is how we do that. So in order to estimate the parameters, we have to estimate 2 out of n inner products, because we have 2 out of n inner products here. They needed to be estimated, plus beta 0. You see, because so it has been shown that in order to find that, let me repeat myself, it has been shown that in order to find this inner product, what we need is 2 out of n inner products from all variables. If we have this value of inner products of all observations that we have, which is 2 out of n computations, we can deal with that. And it is also shown that in order to find these alphas that I earlier said we have n observations to do that. In order to do that, you only need to consider those of the observations that are on support set. That means they are within the margins. So the only observations that are within the margins will be counted. So we really don't need to estimate n of these alphas. We only estimate a subset of that. So I stop the course here. I get back to you in my next video.